Okay, so let's take a simple example. You know, like we had before, this is a typical example. We've got F and we've got G, and we've got, let's say we've got something that is, you know, where we have, let's say the slope is the square root of 2 roughly. G equals root 2f. And so if we were to look at what data gave rise to that, we'd say, okay, we have, you know, we'll have f and g, ordered pairs of f and g, and we'll have something like, you know, f will be 0, 1, 2, 3, 4, 5, 6, 7, 8, and so on. And g will be 0, and then this is going to be root 2, 2, root 2, 3, root 2, 4, root 2, and so on. So everything here is square root of 2 times more. And then implicitly underlying this, the example that we had, that we were considering, we were considering f equals square root of q, and g equals root 2 q, which equals root 2 root q, which equals root 2 f, i.e. this is right here. And so now, if we know the thing that we didn't know, or we normally wouldn't know, but let's suppose we do know, that q, in this case, q equals f squared. So in this case, q equals f squared, so it's going to be 0, 1, 4, 9, 16, 25, 36, 49, 64, and so on. So this is what we want to infer, more or less, and from this data. So this example here is maybe not exactly lined up with how we did the experiment, but let's take a more something more in line with how the data was collected on the experiment. So typically what we're going to have is we're going to have f, and we're going to have g, and we're going to read out some data. So let's say when f is 0, g is 0, we confirmed that for most photocells, when you have them in the dark, they're infinity ohms roughly, or they're as high as the meter can measure, and that's roughly 0. Most of them. Some of them have a resistance offset, like a background resistance that they'll have, or conductance with no light, but a lot of them that you can neglect that. Not always, but quite a bit of the time. So now, let's say we have f equals 1. When f equals 1, then g is equal to root 2. And what we were doing basically is now we're moving over the root 2. So what we're basically doing is we're going to take that root 2 and put that over here now. And we're going to say, okay, by the design of our experiment, we designed it so that when we move that root 2 over here, then this will become 2, and then we move that 2 over here and continue, and then this will be 2 root 2, and then we move the 2 root 2 here, and then 2 root 2, this becomes 4, and then we move that 4 over here, and then when you put the 4 here, this becomes, again, 4 root 2, move 4 root 2 over here, and then, of course, when you move the 4 root 2 over here, you have your twice. So you can see there's a pattern here. You know, you've got 2, 4, 8, 16, 32, 64, and so on. You can see this pattern emerging. And of course, this is going to be 8. This 8 is over here, and this is 8 root 2, and 8 32 is here, 16 is here, 16 root 2, 16 root 2, 32, 32 is over here, 32 root 2, 32 root 2 is here, and 64, and so on. So you can see there's a natural pattern that's progressing here. And what we know in some sense is that 2q, if we look at underlying this, there is underlying this situation over here. Implicitly, we can also add in the columns of q and 2q, and these are the things that we don't know and are trying to solve. But let's say we're looking inside this. Let's say we know these, but that we wouldn't normally know them, and that's what we're ordinarily trying to solve. Obviously, when f is 0, then q is 0 and g is 0, so we've got 0 across the board at the top. And then we've got 1 and 2 here. So we know that this relative q, we might call that q0. We could say q over q0 over q0 if we want to normalize to this unknown constant that we don't know. So we're going to have 1 here and 2 here, and then this is 2 and 4, and this is 4 and 8, and this is 8 and 16, and you can see in a way these are just carrying over, and this top row is just at the origin, but this is where we're really starting. We're unrolling that comparagram starting at 1, starting at f equals 1, or our initial q0 is being assumed. And so we got 4 and 8, 16, 32, 32, 64, 64, 128, 128, 256, 512, 1024, and you can see there's kind of a logarithmic progression here. $4,096, and so on. It just continues to increase. So you can see we've got this kind of logarithmic progression here, and each of these is coming across in this way. And so this is a very, very simple worked example that you can see. And then what we would do is we would plot this data out. We'd try to plot this data and try to infer what the response function of that photocell is. And once we plot this data out, you can see we have here. Take some of it off at the bottom here, make some room, because we're typically going to want kind of we'll have a plot that's sort of like this. We're going to have here, this is Q, quantity of light that comes in, and this is what we're trying to determine, f of Q. And so we're going to have something like, we're going to have Q0 right here, and we're going to have 2Q0, and then we're going to have 4Q0, and then we're going to have 8Q0, and then you can see this is a linear axis, and 32Q0, and so on. So we're going to have this axis here. Now, if I change this axis, label, I take this away here, and I change this to Q over Q0, the reference quantity, then this axis here simply becomes 0 here, and then this is our starting point, 1, 2, 4, 8, 16, 32, and so on. And then the height, up here you can see when we're at F, say, this is going to be 1 right here. And then when we have, when we double the amount of light, what happens over here is when we double the amount of light coming in, this goes to the square root of 2. So that's about 1.4 here, let's say. And then when we double the amount of light again, it's 1 square root of 2. When we double the amount of light again, this goes up to 2. So that's here, roughly. And then when we double the amount of light again, this goes to 2 root 2, which is about, so that's about 2 here. That's 1, 0, 1, 2. And then 3 is around here, and this is going to be about 2.8. Almost 3. That's 2 root 2. And then over here we're going to have 4. See, when Q over Q0 is 16 here, then F of Q is 4. So let's go 3. And then 4 here, and then straight up to here. And then again, when we double it again to 32, this is 4 root 2, which is about 5.6. There's 5 here coming across, and so it's going to go a little bit past 5, a little bit more than 5.5. That's 5.6. So these heights, of course, are, 1. Actually, I'll put them in a different green or something. Let's see, 1, 1.4, 2, 2.8, 4, 5.6, 8, 11, 16, 32, 45, 64, and so on. And those numbers are very familiar from if you have the camera lens, when you have the iris of the camera, they're all increasing by the square root of 2. So they're nice familiar numbers to us. If you're a photographer, you're used to that kind of progression. And now we can see that we have unrolled this function. So we took this function here like this, and what we've done is we've unrolled that comparagram. So you can see we've got logarithmically spaced points along the Q over Q0 axis, and then on the F axis we've unwrapped or unrolled this response function. And so you can see what we're doing here is we're going over, come up, and then down the circle, go over, come up, come around again. And so what we're seeing this pattern where we're call that log unrolling. It's a logarithmic progression. And so you can see we've got this function here known or determined at a very sparse set of points. But as we make that ratio smaller, if we have that f of 1 plus epsilon times q, i.e. k equals 1 plus epsilon, as we let, right now epsilon is equal to 1, so it's f of 1 plus 1, which is times q, which is f of 2q. But as we let that epsilon get smaller, we saw with the light bulbs, we had 6 bulbs versus 5. We have 5 bulbs, and then 6 bulbs is a small percentage increase. And so that we're learning how to use this comparametric data. In fact, I've got my live brainwave data streaming over here. That's coming right off my head right now. That's the BlueberryX.com dashboard. And so we're using all this kind of comparametric equations and sensing and understanding how the brainwaves read to this little brain pod here. It's got this near-infrared spectroscopy scanning my brain. And so it's in this little head-up display. So this augmented reality overlay is all coming from this kind of conceptualization. We're understanding how much light is present. We have a photodetector. We have photodiode. And the nice thing is with a photodetector and photodiode, with the right kind of transimpedance amplifier on the photodetector, and the right kind of transconductance amplifier driving the photodiode, we have kind of linearized this so that f of q is proportional to q, and we implicitly have this comparametric relationship directly. So we see this HDR sensing is useful for a lot of ways, for sensing the brain, for sensing biosignals. There's a massive dynamic range between the light that you blast out into the brain and what comes back. So there's a huge dynamic range. Your heart beats really strong, but then there's other signals that are a lot weaker that we have to pull out of that. So we're going to have a really use case for this. Now, as we make this a little smaller, and we start to have this spacing more finely graduated. So this is a very coarse spacing in this example, but we'll go to a more fine grade spacing and unroll these comparograms at a much finer scale. But the principle here is simply consider this really simple example. F equals square root of Q. So then G equals square root of 2 times F, straight line passing through the origin, and unroll this, just think this through and understand this example, and then go back to Adnan's lecture, where you're going to really, really understand the quantum field theory approach to comparametric